This leads us to the popular methodology, which we talked about in the history of neural networks too, which is known as backpropagation. Backpropagation is a procedure that combines gradient computation using chain rule and parameter updation using gradient descent. Remember, we said we want to minimize a loss function. We said gradient descent is the way to minimize that loss function. But then gradient descent needs computation of derivatives for which we need the chain rule. That's going to be the overall strategy for us to train the neural network. And let's see more details. Let's consider once again the simple feedforward neural network, or what is the other name for multi-layer perceptron. Let's consider once again a set of M training examples given by xy, xi, yi. Let theta constitute all the weights and biases in the neural network. Let the mean square cost function for a single example be given by, let's assume that h theta of x corresponds to your neural network at this time. Okay, that's your neural network. And y is the expected output, because we know that that's the output for the corresponding training sample. So given one particular sample x and its correct label y, your loss function is given by h theta of x minus y whole square. Remember, we said mean squared error. We are not doing the mean here because it's a single sample. We are going to introduce, we however multiply it by half purely for mathematical simplicity. You'll see why a bit later. But the reason why it doesn't matter is because we are interested in the theta that minimizes the loss function and not the loss function value itself. So whether we minimize half of the loss function or the full loss function, it's the same theta that will give you the minimum in both these cases. And so it doesn't matter to us, and we introduce that purely for mathematical simplicity. Now the overall cost function across all examples, we saw the cost function for a single example. The overall cost function across all of these examples is going to be given by 1 by m summation over all m's L theta xi yi. So the same L function summed up over all training samples and then averaged. And L theta of xi yi can be replaced by your mean square error definition. That's the overall cost function that we're going to go with. We still have to compute the gradient, but that's the overall cost function. Let's now define the notations to be able to define the backpropagation procedure completely. Let's assume that there are NL layers in the neural network. NL layers in the neural network going from 1 to n sub L. Let's denote the activation of a node I at layer L as A sub I Lth layer. Rather, remember, every layer has a set of neurons. We are now looking at the ith neuron, which is the node I that we are talking about, and we are looking at the Lth layer of neural network. And the activation is simply the output of that particular neuron. Remember, every neuron is now individually like a perceptron, and we already said that for a perceptron, instead of having the threshold function, we can have activation functions such as sigmoid, hyperbolic tangent, so on and so forth. The output of that function is what we denote as an activation on that particular node. Remember, again, to repeat, that node is like a perceptron. And in the Lth layer, we call it A sub I, superscript L. We denote the weight connecting node I in layer L and node J in L plus 1 as Wij in the Lth layer, and the entire weight matrix between layer L and layer L plus 1 is denoted as WL. For a 3-layer network that we saw earlier, a compact vectorized form of a forward pass can actually be written like this, and hopefully this will give you clarity on the entire procedure. Given an input X, you take the first layer's weights and biases, and you get the output on the next layer, that's Z superscript 2, second layer. You take Z and apply an activation function F, and the output of that becomes A superscript 2 in the second layer. We're just going to assume one neuron in each layer just to make the notations simpler, but you can extrapolate this when x is a vector, z is a vector, a is a vector, so on and so forth. Now you take the activation, take the next layer's weights, which is given by W2 and B2, and you do W2, A2 plus B2, you get Z3, that's the Z in the third layer. You apply an activation function on that to get A3, which is the output in the third layer, which is also the output of the neural network. In this case, the function f denotes an activation function, such as sigmoid, ReLU, identity, so on and so forth. Let's now try to see what backpropagation actually does while training a neural network. During the forward pass of a neural network, so every neural network can now be divided into a forward pass and a backward pass. Forward pass is when you give an input to a neural network and you propagate that input through the weights of the various layers and you get an output at the output layer. You call that the forward pass. Now, based on the output at that output layer, you would get a certain loss. Based on the loss function that you chose, you expected a certain output because it's training data. You know what the expected output should be. You know what the neural network is throwing out. The difference between the two, or whatever loss function, it need not be just difference, you could use other loss functions. That loss function of the output is what we now have at the last layer. And we now have to use that loss to compute the gradient for each of the weights in the neural network. That's the backward pass. Okay. So during the forward pass, we simply compute each layer's outputs and move from left to right. During the backward pass, we compute the loss in the last layer and move from the rightmost layer to the leftmost layer, starting from NL all the way going to the first layer. We compute gradients going from the rightmost layer to the leftmost layer, and once we have all the gradients computed, we can use gradient descent to update the parameters. How do we do? Current new parameter is equal to old parameter minus eta, which is the learning rate or step size, times the gradient with respect to that parameter. Now let's also try to see how this specific propagation of gradients happens from the last layer till the first layer. The first thing is we denote for each node an error term that denotes how much that node was responsible for the loss at the output layer. Let's imagine now that the error term at the output layer is given by error term at the ith node in the output layer. Remember, even the output layer could have multiple output nodes. The output need not be a single value. You could be giving a vector as an output too. For example, you may want to predict at what location an event may occur next. So let's say you want to use some logic, you want to predict using machine learning to predict where the next FIFA World Cup will happen. Okay? So you may want to predict that in longitude and latitude, for instance. Right? So that could be the two outputs that you may want to predict. So your output layer could have many values in that layer. So delta I NL is the last layer, delta I is the delta or the error for the ith node in that layer. And the error term at that output layer is given by minus yi minus ai NL into f prime zi NL. How did we get that? This is simply the gradient of the mean square error. Remember, we said we are taking mean square error as the loss function. We simply take the derivative of the mean square error. So in our case, it's going to be yi minus ai. Let's assume that's your final layer's output after applying the activation function, whole square. And remember, we said we'll have a half for convenience. I mean, when you take a gradient of this with respect to ai, you're going to have minus 2 and 2 would get cancelled, and you would have yi minus ai NL. Okay, that would be your gradient of the mean square error. But remember that ai itself is a function of zi. The way we defined it, zi, you apply an activation function f and then you get ai, which means in the chain rule, you would then have f dash of f prime of zi NL. So where AI is given by f of ZINL. So that's going to be the error term at the output layer. Now we're going to claim that the error term at the hidden layer is going to be given by this quantity, and let's try to find how. For the hidden layer, we have to rely on the error terms from the subsequent layers. So once again, let's assume that the error term at the output layer is given by this. Now the error term at the hidden layer is given by sum of the error terms in the next layer, which means delta I in the nth layer is going to be given by delta j in the L plus 1th layer multiplied by wij's in that layer that goes from L to the L plus 1th layer. Sum them up over all the number of neurons, let S sub L plus 1 denote the number of neurons in the L plus 1th layer. So you add all of them up into f prime of ZIL for that particular node. Okay, remember that's again f prime of ZIL is simply the derivative over the activation function at that particular node. Remember, this is the reason why we said it's nice that the sigmoid function is continuous and differentiable. Okay? Because we need this derivative across the activation function to be able to compute your chain, rule. Now you could ask me, why am I multiplying it by the weights? Because that's the contribution that this node had to the error on that particular node in the next layer. The ith node contributed by wij times to the error at the jth node in the next layer. Okay, that's what we are denoting it by the sum of errors. As we just mentioned, f prime denotes the derivative of the activation function. For a linear neuron, f of x is equal to x, derivative is 1, simply that term won't matter for the rest of the computations. But for a sigmoid neuron, f of x is equal to sigma of x is equal to 1 by 1 plus e power minus x. The derivative turns out to be sigma of x into 1 minus sigma of x itself. Right? Suppose you already know it. For those of you who did assignment 0 in this course, you should have seen it. But you can also work it out as homework. So the way we are going to train the full network now is we perform a feed-forward pass, computing the activations for all layers. For each output unit I in the set of neurons in the last layer, denoted by NL, we compute the error, which is dou NL, which is the derivative of the loss function with respect to the final activation, into the derivative of the final activation with respect to ZNL, which was before applying the activation function. And then on, for the previous layers, each delta L can be written as WL transpose times delta L plus 1. Remember, now we have written this as a matrix, and that's why the summation disappeared. And this WL transpose matrix times this delta L plus 1 vector would ideally give you the summation that you're looking for, that we talked about on the earlier slide. Having computed these deltas for different layers, remember delta is the contribution of every node to the error. We are now going to use those deltas to find out the partial derivatives of the loss with respect to every weight in the neural network. How do we do it? Very simple now. It's going to be defined as the loss or the gradient of the loss with respect to every weight in any layer L is simply given by take the delta L plus 1, the contribution of the error term in the next layer, and multiply it by activation of the nth layer. Let's try to understand why this is correct. Let's consider a neural network. Let's say these are some layers of a neural network and these are nodes. Let's assume that there are many more layers before this, but this is the last layer, which is NL. This is the penultimate one, NL minus 1. This is one before that, NL minus 2. Now, in the last node in the output layer, remember, let's draw that a little bit bigger. So this side is going to be, this W is what we want to compute it with respect to the gradient Z. And when you apply the activation on Z, it becomes A. So the way Z and A are related, is f of z is equal to a, where f is the activation function of your choice. And this a is finally used to compute your final loss function. Remember, we said it is y minus a whole square, right? Where a is the output and y is the expected output. So to compute the gradient with respect to w, right, let's erase unnecessary information here. So to compute dou L with respect to dou W, for the moment let's consider this weight, that's what we're computing with respect to. We apply chain rule. Chain rule tells us this is dou L by dou A into dou A by dou Z into dou Z by dou W. Now dou L by dou A is exactly this term here. That's the derivative of the loss with respect to A. Dou A by dou Z is exactly this term here, which is the gradient of the activation function f prime. Dou Z by dou W is now what we have to compute. But we know now that dou Z by dou W is nothing but the activation in the previous layer. So let's probably write it this way. The activation is right here. The previous layer Z would be here, and activation is applied, and A is what would come here. Remember, for WL will go from AL to ZL plus 1. So if you want to compute the derivative with respect to WL, dou Z by dou WL will simply be A, the previous layer. Why? Because AL into WL will be ZL plus 1. Okay, we are simplifying it and talking in terms of scalars, but you could now expand this to all the other nodes in that layer and also write it as a vector. But that's the broad idea. So once again, if you instead had a delta that was to, let's assume now that we want to compute the gradient with respect to a previous layer. Let's call that W NL minus 2, right? So one of these weights. Once again, it's going to be the same. You just have to keep computing the chain rule over and over again, and you will find that the chain rule will give you delta at this node as the contribution of that node to the error. Now you simply have to differentiate that with respect to W, which will give you the activation in the previous layer as the additional term. Okay. That gives you your gradient. Work it out a bit carefully and you'll follow that this is fairly straightforward. Now this gives you the gradient with respect to W. Similarly, if you notice the second equation here, that has the gradient with respect to the bias. It is exactly the same thing where the activation is 1. Remember, because the activation that goes into the bias in any layer is going to be 1. Remember once again that a bias could be there for every layer, not just the first layer. Could be there for every layer, but that value will turn out to be 1. So what have we done? To summarize, we have computed those deltas that are the errors of how each node contribute to the output, and simply use that to make our chain rule computation simpler. We could have instead not written out delta and worked out the chain rule, but you would have got exactly the same value. Delta gives us a placeholder to hold how a particular node in any layer contributed to the error, and now it's very easy to compute the gradient using that error for a previous layer's weight. That gives us our final algorithm for training a neural network. Let's go over it. So let's assume that delta W and delta B are set to 0. Just a minor clarification here to differentiate delta and grad. Delta defines the change in a value. Grad defines the gradient of a function with respect to a value. Okay, so please keep this in mind in the notations. So delta W and delta B are the change that we're going to make to W in a given iteration of gradient descent. Let's initialize that to 0. Then for each data point that you have in your training data set, you forward propagate that data point, you compute the error, compute the loss, compute the gradient, and use backpropagation to compute the gradient with respect to every weight in the neural network. That gives you grad L with respect to theta. Now your delta theta that composed of delta W and delta B, you increase that by this much gradient now. And you would keep going this over a for loop for every data point in your data set. And that gives you the total delta theta that you have, delta W and delta B. That's the total change that you want to make to your W and B. Now to update the parameters using gradient descent, you're going to say WL in the current step is going to be WL in the next step is going to be WL in the current step minus eta, which was your learning rate or step size, into 1 by m times change of W. 1 by m is simply to average the gradient across all of your data points. Remember here, we were summing up the gradients for all of the data points. Now we simply want to divide by m to average the gradient across all of your data points, and that tells you how your current weights had an impact on the loss across all of your training data points. That's the gradient that you're going to use to update W. Then you'll get WL at the next time step, and similarly B at the next time step, and you keep repeating this until convergence. Remember, convergence is when grad loss with respect to W and beta becomes 0, or you get all points right. In practice, this may be difficult. How do we handle it in practice? We'll talk about it in a later lecture. For further readings, please read chapter 4 and chapter 6 of Deep Learning book. Not all sections in these two chapters may be relevant, so I'd advise you to read what is relevant to the sections that we've covered so far. Also go through the Stanford UFL tutorial and the CS231 endnotes. The links are right on this slide if you're interested.